Hello everyone, welcome to this video, and in this video we'll be coding a neural network from scratch in PyTorch. Watch the video till the end because only then you'll be able to understand the full concepts. So let's get started. Okay, so let's see what we will cover in this entire video. First, we will learn how PyTorch treats every model as a computation graph. Second, we will be talking about a technique called as autograd, which helps us to calculate the differentiation of each function very easily. Third, we will be talking about how to implement a neural network using PyTorch libraries. Fourth, we'll be talking about how to load the data. Once we have the architecture up, we need to know how can we load the data itself. And finally, we'll be talking about how to bring all of these pieces together to finally write a training loop. So do not miss the end. And one thing I would request all of you is to keep pausing the video and writing the code yourself side by side. This will help you to learn and get the intuition of the code very nicely. Okay, so let's get started. Let's imagine that we want to predict whether it will rain tomorrow or not. And the only data point that we have with us is the temperature. Let's imagine that we implement a simple logistic regression model. So for people who don't know what a logistic regression model is, you can imagine that this is a model which will take some input. We are giving it input the temperature and it will output a value between 0 and 1. And we can treat this value as the probability of will it rain tomorrow or not. What we want to do here is that we will give the input temperature, let's assume we call it X, to our model, and our model will have a trainable parameter called as weight. Let's call this as W. Now what the logistic regression formula is, it will basically calculate a value Z which will be equal to W into X, plus there will be one more term called as the bias, plus the bias. This value Z can be more than 1 and it can be less than 0 as well. So to bring this value between 0 and 1, we apply something called as the sigmoid function. This is denoted by this particular formula, 1 divided by 1 plus e to power minus z. Any value you input in this function, it will lie between 0 and 1, the output. So that's why this function is so useful to us. What we eventually want to do is, let's say we have a first training data point and we say that the temperature of the city was 40 degrees Celsius and the probability of raining is 1. So now what our model will do, it will try to run and learn from all of these training data. Let's say we input the value 40 and our model is giving, and our model is then multiplying this value with W and then adding a term B here, and after we apply the sigmoid function, we get a output of, let's say, 0.4. Now we have to tell the model, no, this is wrong. We need the output to be near 1, right? There is some difference between the expected output and what the model is outputting, right? So we can capture this using a loss function. So generally in classification, we use something called as the binary cross entropy. We won't go into the details of this, but just get a feeling that you have a loss function, which will help to train the model better. So the next time we have to signal to the model that you had outputted 0.4, but really the value should have been near to 1. right? You go ahead and change your value of the parameter w and b such that the output that we are getting should be closer to 1. If you think intuitively, you should calculate how much is the change in the loss with a small change in your parameter w and a small change in your parameter b. So if you are able to calculate this value, you will be able to nudge the loss towards 0, and that's what we want. Okay, now let's see how PyTorch treats this entire process. We have an input x, we have a trainable parameter w, and then we are multiplying it. So PyTorch will treat everything as a computation graph. We multiply this and then we get an output u, let's say. It will be x into w, right? After this, we add a trainable term called as bias. So this node will be a plus term. This was a multiplication term. And we finally get something called as z, which is u plus b, right? Now, after we get z, we transform this z through a sigmoid function. So let's say we call it a. And finally, we will go ahead and calculate the loss from this. And in the loss, we will be inputting the actual value y, which we want, and a final value that the model has predicted loss, right? So internally, PyTorch implements our computation graph like this. Okay, so now you might be thinking, how are we calculating the losses, right? So using this first node, we will calculate dl dA. So a small change in loss given a small change in A. Then using this node, we can calculate a small change in A given a small change in Z. Now in this node, we can calculate a small change in Z given a small change in U. And finally, here we can calculate a small change in U given a small change in X. And also a small change in U given a small change in W. How is this helpful to us? So finally, we wanted to know, right, what is this particular value? Like, if we change the value of W, how will the value of loss change? You can use the chain rule and finally multiply all of this value. You will be multiplying dA given dz into dz given du into du given dw. So for people who don't know chain rule, we know all of these 4 different values, right? It is very easy to calculate. And you will see that dA gets cancelled, dz get cancelled, du get cancelled, and finally we only have left dl divided by dw, and that's what we wanted. So this is how amazing chain rule and the entire backpropagation algorithm works. Now we will see how to implement this in code. So let's start with it. First, we will import Torch, and then we can quickly check what is the version of Torch we have. Okay, so we see that we have 2.8, and it can differ according to your environment and the time you're actually implementing your code here. So first, let's define the value y. So let's assume that in our example, it is going to rain tomorrow. So that's why we are giving y as 1. Now let's give, so this is basically our temperature. So what we can go ahead and define is to be, we took it to be 40 degrees Celsius, right? So let's take it 40. Now, what is our W1? This will be, let's say we can start with any random value here, right? 2.2, let's say. And then we'll go ahead and implement the bias, which is let's start with a value 0, 0, 0.0. And then the definition of z was x1 into w1 plus b, right? And the value of a was torch dot sigmoid, and we are inputting z here, right? Now we need to calculate the loss as well, right? So for that, we can import an internal library which is called as torch.nn.functional, and let's call this as f because we don't want to write it again and again. So this library already has a very good implementation of binary cross entropy, and we will calculate the loss using that. So we will just say this is binary cross entropy, thank you Copilot, a comma y, right? And then we'll go ahead and try to print the loss. Let's see if this works or not. Okay, so this works. So apparently our first loss is 0. Let's say if we reduce the temperature to 0.1, 0.2, let's say, then you see that the loss is increasing, right? Our function is properly implemented. Now, you might be thinking, how can we go ahead and implement the different gradients, right? So for that, we can use a library called as AutoGrad. This library helps us to implement the differentiation of each functions very easily. From torch.autograd, we can import grad. Now let's see what is the power of this particular function. Now, one more thing you need to understand here is that for this function to know that this is a trainable parameter, you need to mention that this particular parameter requires a gradient. So this will go ahead and tell PyTorch that you have to track the differentiation of this function and you have to calculate and accumulate the gradients for this. So why are we doing this? We are doing this because W and D are the trainable parameters of my entire network here. And we want to make sure that we are calculating the gradients for these two parameters throughout the entire training process. So how this will help us is, once we have mentioned that requires gradient equals to true, we can go ahead and see and print that what is the gradient of the loss with respect to W1. You can go ahead and write it like this: loss W1, and you also have to write retain graph equals to true, because if you don't write this, the computation graph will be gone after this. So we don't want to have that, right? Why are we getting this error? Because we did not run this particular cell, right? And after we run this particular cell, let's try to go ahead and print this thing, and you can see that the gradient of this particular variable is minus 0.078. So that is pretty awesome, right? PyTorch does all of this thing just using this very good simple function called as grad. But one thing that you will notice here is that you won't keep writing this entire line for each parameters, right? Because there are a lot of different parameters in a particular neural network, and you need to make sure that everything is implemented very nicely. To implement this, we have a very powerful line which is called as loss.backward. You can just run this line, and what this line will do is it will go ahead and calculate the gradients for all the parameters for which you have mentioned requires grad equals to true. And how you can access the gradients of each particular variable, you can go ahead and print the particular grad value for that particular variable. Even if you do this, you're getting the same output. So you don't need to actually go ahead and write this particular loss for every variable. PyTorch does this using just one single line, and that is loss.backward. Okay, so now we fully understand what a computation graph is and how are we calculating the gradients of each parameter. So now let's see how we can implement a neural network architecture. So now let's assume that instead of just one input, we also have the humidity of the place. Okay, we have the temperature and we also have the humidity. What a neural network will do is that it will have multiple hidden layers in the middle of the network. So let's assume we have 30 neurons in the first layer, we have 20 neurons in the second layer, and in the final output layer, we just have 2 neurons. And what this 2 neuron will represent, this will represent probability of raining tomorrow, and this second one will represent probability of not raining tomorrow. Okay, and how a neural network internally looks is that it will have 30 different circles or nodes in the middle here, and it will also have like 20 different nodes here as well, and each of these particular neurons will be fully connected to every other neuron. What I mean by that is that this particular first neuron, it will be connected to each of these 30 different neurons. So you can imagine like how many different parameters we'll have in a neural network. But PyTorch makes it very, very easy to implement a neural network. So let's go ahead and implement this in code. Okay. So we cannot write the entire layer, the entire bias, the entire nodes from scratch here. What we will do is we will make use of a torch library which is called as nn.module. So first let's define a class. Let's name our class as my neural network, and then it will implement from a torch module, which is torch.nn.module. Now you have to remember two things while implementing a neural network architecture. First, you have to define the init function, and second, you need to define the forward method. You don't have to go ahead and implement the backward method because backward method can be easily computed using that particular line called as loss.backward. So let's go ahead and implement the init function. The init function will take self, what are the number of inputs, what are the number of outputs, and then we can first inherit. We can then inherit the superclass. This will help us to use a lot of functions which are already defined in the torch.nn.module. Now just let's go ahead and define our layers. So as we saw that we had implemented two hidden layers, right? What we can do is we can make use of a class called as torch.nn.sequential. This particular class will help us to easily define the layers. So let's go ahead first define the first hidden layer. As we know that the first hidden layer was a linear layer, so this linear will define a fully collected layer. We just need to define like what is the number of inputs, which is number of inputs taken by our particular class, and the first layer will be connected to 30 different neurons. And let's say we also apply an activation function. We won't go into the depth of activation function right now, but you can imagine that this is kind of a function that is applied on top of the output itself. Now let's go ahead and define the second hidden layer. Again, we will go ahead and write torch.nn.linear. Let's say this 30 is connected to 20 different neurons afterwards. That's what we saw in the diagram as well, right? And then we also apply a ReLU function here as well. And finally, it's time to define the output layer. So the output layer is defined by 20, comma, how many outputs we have? This number of outputs. So this is how we can define the layers of a neural network. And one more thing we need to implement is the forward function. It will take input as x, which is our temperature and humidity, and then we can basically define the logics. It will be self.layers, and all of this x will be passed to this entire layers, and it is very simple to just implement this, right? And finally, we can return the logics here, and that's how you can define your neural network class. It was pretty simple, right? And to declare your model, you can just go ahead and say that I want to make an object of my neural network class where my number of inputs is always 2, my temperature and my humidity, and my outputs is always 2. So you can easily declare your object here, and let's see and print how the model looks like. Awesome, right? It is a sequential model where the first layer is a linear layer, the number of input features is 2, output is 30, and then again the number of input features in second layer is 30, output is 20, and then similarly final layer has 20, 2. So this is how you can simply implement a neural network class. You just need to inherit from the nn.module class, and you need to implement 2 functions, which is the def init function and the forward function. So now you know how to implement a neural network in PyTorch. Okay, so now let's see how we can implement very efficiently our data classes. First, we will define our training features. So let's assume that we have 5 different data points. The first data point, like for clarity, I will just mention 1.0, 1.0, and then for the second sample, we have temperature 2.0, humidity also 2.0. This is not like real data, I'm just mocking up some data here. 3.0 and 4.0, 4.0, and finally the fifth data point will have 5.0, 5.0, right? And let's assume that we observe that on these data points, right, for the first 3 days there was no rain, but as the temperature and humidity increased, we had rain on the last 2 days. This is what we want the model to learn. Okay, we're mocking up some data, and let's say we are also testing on 2 particular data points. The first data point is basically, let's say we have temperature as 0.5, humidity is also 0.5, and the last one, let's say we have temperature of 10 and humidity is also 10, right? And according to our hypothesis, right, let's assume it does not, and on the second day where the temperature is high and humidity is also high, it rains. So let's say we have all of this data, right? Now our responsibility is to implement we have to make a data set out of this. How we can do that, right? So we can use a very useful library called as dataset. It will be present in torch.utils.data, and I'll tell you how to implement a dataset class. So let's say we call it my dataset, and it will inherit from the dataset class that we just imported. Now, while implementing any dataset class, we need to take care of 3 different things. You need to first define an init function. Secondly, you need to define getItem function. What this function will tell how can I access one particular data point in my data set? And thirdly, we need to implement a length function, which will tell me what is the particular length of our entire data set. So let's go ahead and implement this. Okay. So first is our init function. It is taking input as x and y, which is basically our features and our labels. Let's call this y, right? Now the second thing that we need to implement is a get item function. So what this will do is it will take input as one particular index. So basically we are asking like, what is the data which is present in this particular index? And it will return 1x. So how can we get 1x? We can just access the element in an array, right? So we can just say that it's in self.features.index. Similarly, we'll do this with y as well. It will be labels index. And then we can go ahead and return this 1x, 1y. This is how you have to implement the get item function. You take input as an index and then you give output one feature and one label. And finally, we need to implement the length class. This is basically telling what is the length of a particular data set that we have. So we will go and just take the shape of our labels and we want the first value of it. And let's go ahead and try to run this. Okay, so now we were able to define our myDataset class, and now let's try to define two objects from this particular class itself. So we can just simply write myDataset, what are my features in train? It's xtrain that we defined on the top, and ytrain are the labels that we want to train on. And then we have to define the test dataset. This will be taking input as x test and y test, right? So this is so awesome, right? How this will help us is that we have now defined our data set. Now one more last thing is left is we need to give input these data sets as batches. So what happens generally is that we have a lot of rows in our data set initially, but for training the model, we will give the model batches of examples. We cannot train the entire model on the complete whole rows. So now for that, we have to take help from a class called as data loaders. You can easily import data loaders from torch.utils.data, and I'll show you how we can go ahead and implement our data loader. First, we will define a train loader. This will help us to load our training data set. And what this will take is that we need to mention what is our data set. So this will be our train DS that we have defined on the top. And then we need to mention what are the number of batches. For that, we can mention the batch size that I mentioned above. So the batch size, it's 2. Now let's go ahead and implement the test data loader. This will be like a similar thing, how we implemented that. There was a small error here. And this is how we implemented our train loader and test loader. How can we iterate over this data loader, right? So for this, you can simply write for index, it is giving me the features and the labels. And how you can do this is by using a function called as enumerate. So you can enumerate on the data loader and you can go ahead and print. Let's say we want to print that the current batch size is this, and this is the features, and this is the labels. Let's try to see this. And it is so awesome, right? We are able to see that for batch 1, how many inputs are there? We have 2 inputs, 1, 1, 2, 2, and the output is 0, 0. And similarly, we have batch 2, and in batch 3, there is only 1 data point because we only had 5 examples in total. So now you know how to implement a data loader and a data set for your own data. Now, let's start coding the final training loop. The first thing is obviously we need to define our model. Our final model that we want to implement is a neural network again, and it will be taking input as 2 and the number of outputs will again be 2. Okay, so one more thing that we require for a training loop is an optimizer. What this optimizer will do, it will go ahead and finally do the computation on our trainable parameters. We have already computed the gradients using loss.backwards, and then this optimizer will decide how much subtraction or how much addition do I need to do in my parameters, how much tweaking do I need to do, so that in the next step I am able to predict something better. We are not going into the deep of maths of this, but you can easily implement this using torch.optim.sgd. Now we have to mention that, like, what are the parameters that you have to apply the optimization on. That is obviously our model.parameters. And then we also mentioned something called as the learning rate. When we calculate the gradients, how strongly do we want to learn? Someone can be very fast, right? Let's say in one batch, it gives me a signal that no, you have to increase the model parameters. So I have two options. I can increase it slightly, or I can increase it at a very huge value in that particular instance as well. So this is something that is controlled by the learning rate. Now we can define the number of epochs. This is basically the total number of times you are going over your entire training data set. Now we can implement a for loop here. How many times we want to go? It is number of epochs, right? So the first thing that we want to do is we want to set our model in training mode, and then we can implement our training data loader. So for a batch index and some features and labels, we can use the enumerate function, and we will use our train loader that we had. What is the first step? The first step is to calculate the logits. We'll just go ahead and pass the features into the model that we have defined above. And how to calculate the loss, right? As we saw above, we can use the cross entropy function, which is already implemented in nn.functional, and we will input the logits and the labels here. So what we have done here is that we have taken input some features, and then we passed our features to the model that we defined here. We got some outputs, the model predictions, which is called as logits, and then we are passing it to the loss function. So we have done a one particular forward pass here. We know that this is the input, this is the model output, and this is the loss. Now, what we have to do is we have to calculate the gradients. We need to calculate how much change each parameter should do in order to decrease the loss. And you can do this using this line loss.backward. And finally, you can update the different parameters using this optimizer.step line. and then we can go ahead and log our particular epoch. So we can say that we are standing at epoch, and let's say this is the train loss we are seeing currently. This is something that we can track. So we will just write it as loss here. Okay, yeah, so this is how a training loop can be implemented. Let's see if it works or not. Okay, so it has started executing. Okay, so if you see in the output, there were 3 batches in each epoch. How many batches we needed? We needed 3 batches because we have 5 data points, and each batch had 2 data points. That's why every epoch has 3 entries here. This is batch 1, batch 2, batch 3. So this is how you can implement an entire training loop and a neural network in PyTorch. And I will be sharing this entire code in my Kaggle profile, and I request all of you guys to go ahead and type this out yourself. Bye bye. See you in the next video.